I said that I'm sure you know about it.
No, I said you may have heard about it, but if you haven't, then...
Okay. Sorry,
Let's go.
Okay, client-side validation. You may have heard of zkcoins. I think Robin mentioned it on a podcast recently. It's also in some of his work. So I'm going to talk about what client-side validation is, why it's interesting, how we can use zero-knowledge proofs to make it better, and then what I'm working on now, depending on how fast it goes and how much time we have. Okay, so we all know about blockchains, right? Blockchains, we've heard of them, were invented originally to solve the double spending problem, right? So you have me, I'm trying to pay Alice, I pay her, I send her some information, and then I also try to pay Bob with the same money. Alice and Bob need some way to reconcile payments to make sure I haven't paid them with the same money or created money out of thin air or any number of different variations of this failure mode.
Mm-hmm.
So the simple solution is we would use a trusted third party. They would collect all the transactions, they would make sure that they're valid, and then we check, they just attest to their validity. What Bitcoin was able to do is devise a decentralized protocol for accomplishing the same goal. So everybody broadcasts their transactions into this decentralized network, and even if some of the nodes in the network are Byzantine, or they're trying to disrupt the consensus protocol, everybody is able to eventually arrive at a list of all of the transactions that are valid, and yeah, so that's basically the story of Bitcoin. What's the problem with this? Well, we have to put all of the transactions on the blockchain, right? So we have like diagrams. Blockchain. It's like and then these contain transactions, right? Okay. The problem is the transactions are in the blocks. The transactions reveal all of the information about the transaction, because you need to know the transactions in order to check that they're valid. So specifically, it has the amounts of money involved, who's paying who, all of this information. And the transactions themselves are sizable, potentially, right? I mean, this basic concept of the blockchain has been like adapted to many different contexts. Things like Ethereum, transactions can be really big. Yeah, so the core idea of client-side validation is that we don't actually have to put transactions on the blockchain in order to prevent double spending. All that we have to do to prevent double spending on the blockchain is to put some sort of proof of ownership so that other people can't spend your money. Some sort of coin identifier to identify like what money is being spent.
As long as you have a sequence, you cannot double spend.
Huh?
As long as you have a transaction sequence, you cannot double spend.
Well, I mean, you have to verify that the transactions are valid. Like, they could be invalid transactions that you have in a sequence. But if you have a sequence of valid transactions, then there are no double spends, sort of by definition, right?
Okay.
But to prevent double spends, all we're trying to do is make sure that a single coin is not double spent. So in addition to a proof of ownership and a coin ID, normally we'd put a transaction. But instead, we can put a hash of a transaction. Hashes of transactions are smaller than transactions, typically.
Typically, yeah, there actually are exceptions to keep going.
And this, so just so we're all on the same page, this ensures that this coin can't be double spent. As long as we have a sequence of this sort of triple of things, a proof of ownership attached to a coin ID and a transaction hash, if I tried to spend the same coin twice, either the proof of ownership would be wrong because I didn't own the coin, or maybe I do own the coin and I try and spend it with two different transactions, but then we'd be able to identify the coin ID and the transaction ID are different, so that would be an invalid sequence of spends. The point is just that we can replace the transaction with a hash of a transaction on the blockchain. But this introduces a problem. We're able to prevent double spends this way, but we're no longer able to ensure the validity of the transactions. I could just put garbage like this on the blockchain and there's no transaction, or the transaction is invalid. So, what do we do instead? We put all of this on the blockchain. All of this goes in a block now. And when I want to pay you, I simply provide the transaction out of bin. So Alice paying Bob, and then there's like blockchain. Alice sends the hash of the transaction to the blockchain, and she sends the transaction to Bob. And then Bob can check that this transaction, that like exists some hash in blockchain, such that hash of transaction equals the hash. So Bob can take this transaction and check it locally for validity, and he can check that the hash is on the blockchain, and he can check that this coin ID hasn't been spent to any other transactions. So he can check that the coin hasn't been double spent, but there's still a problem. This transaction is not valid in isolation, right? It's only valid if its inputs are also valid. So transactions form this graph, right? We suppose this one has like 2 inputs and like 3 outputs. These are also coming from other transactions. And this transaction is valid if and only if inputs valid and like there's no new money created or something. So there's like the local part of transaction validity and the global part of transaction validity. So there's all of these historical transactions, and since we haven't put any of them on the blockchain, if Alice wanted to convince Bob that this transaction is valid, she would also then have to send like transaction prime and transaction prime prime, but then they also have preceding transactions. So you get this kind of exponential growth backwards in time as the money mixes together, and it sort of just grows to encompass all of the transactions that have ever occurred. So that's, a problem. We don't want that. And this is sort of like the state of client-side validation, more or less, before like the introduction of zero-knowledge proofs. But you would agree like something like this would work if we sent all of the transaction history and Alice could prove to Bob that this transaction really is valid. Like all of these transactions are on the blockchain, they're hashes, and they all balance as you go through the chain and all of that. Bob would be convinced that this transaction is valid. Because, by the way, that's what Bob would do to assess the validity of, say, a Bitcoin transaction. I mean, he probably would sort of pre-compute all of this, but if he were just doing it from scratch to verify a transaction, he could do it in like a breadth-first kind of backward search.
That is how wallets do it, isn't it?
I don't know. I mean, if you have like a state and you know that the current state is valid, you just have to check membership in the UTXO set, which is not recursive, but implicitly yes.
But I suppose if you spin up a wallet, if you spin up a Bitcoin node in order to find out if some money someone sent you is valid, you're kind of doing this in reverse.
Yeah, pretty much. Okay, so we have this big transaction history. It's defined recursively, and it grows exponentially backwards. We have a really great opportunity to use recursive zero-knowledge proofs to compress this transaction history. So what does that mean? We can define a proof of transaction validity. And what is the proof going to show? The proof is valid if for public input hash of transaction, or maybe transaction, just transaction, transaction inputs and outputs balance, dot, dot, dot. That's like the local condition, right? That's easy to check. We just check all the outputs, don't create new money. But then, instead of recursively verifying the transactions, we have proofs of the previous transaction. So you have like proof prime and proof prime prime are valid. So we define a proof of transaction validity recursively by verifying proofs of the previous transaction's validity. The key property here is that producing this proof takes time only dependent on like the size of the transaction. Right? It's not going to take time dependent on the whole transaction graph because we already have these proofs, right? When we get paid, instead of sending all of this transaction history, or I guess when we pay somebody, we're going to send them a transaction and a proof of the recursive transaction validity. So this proof attests to the proofs of its previous transactions, which attests to the proofs of the previous transactions, and so on. And the nice thing about this that I didn't even really mention in this case is that you get privacy, not quite, but basically for free. Here, you have to reveal the incoming transactions. I have to say transaction spends an output from transaction prime and transaction prime prime, and then you know where the money's coming from, and so on. Here, Pi maybe doesn't say anything about the inputs of the transaction. Maybe this is a hash of the transaction, and it has like your output. So the public inputs to the proof are just like this transaction, whose structure you know nothing about, has an output that's spent to you, and it's valid, and that's it. And you can define this entirely locally in terms of the transaction validity. Almost. There's one part that I haven't mentioned, and that's that we also have to check that the hash of transaction prime and transaction prime prime, let's get that up, are in the blockchain. So this part is a little bit subtle, but just assume for now that people are running the blockchain software and they have established a history of valid transactions such that no coin ID is double spent. Checking that these these hashes appear on the blockchain and they're associated with sort of like a valid spend means that you haven't like double spent an input basically. But in any case, I think that the important point is just that transactions are able to recursively verify their previous transactions in the context of a given blockchain. So what is the effect of doing all of this? Well, it turns out that this object is about 64 bytes if we compress it, so it's about a signature. And that is all you have to do on-chain. So for any transaction of arbitrary size, you just put 64 bytes on-chain. There's a subtlety that I haven't really discussed, which I could get into if people are interested in, but there's this version that has a coin ID, but you could also imagine you have like an account ID, like an account state N ID or something like this. So rather than there being a coin that goes from unspent to spent, you have an account that just moves forward in time, and you nullify account states instead of nullifying individual coins. That's necessary to get the 64 bytes per transaction. And what's cool is that we can do this. Like proof systems are good enough to do this, like in real life now. There are projects that are very similar to this, like
RGB is very similar.
I don't know. Yeah, in some ways they don't have snarks. So RGB doesn't do the proofs bit. It sends the transaction history, is my understanding. I don't really understand how RGB works entirely. It seems complicated. Taproot assets as well, also known as Taro, is a client-side validated protocol. So they're sort of doing a similar thing where transactions are verified by clients, not on the chain. But they are also sending transaction histories, or they have hacks around it. To the best of my knowledge, in Bitcoin world, nobody is using this recursive zero-knowledge proof construction for transaction validity proofs in a client-side validated setting.
Why is that then? It seems obvious.
Bitcoiners are kind of dumb.
A little slow.
So, look, the client-side validated stuff did, at least the first person I know who wrote about it is Peter Todd, so that is in Bitcoin world. And part of the reason is because snarks were not performant enough in 2016 when this was like being originally thought about. Why hasn't RGB done it, or Taproot assets? I don't know.
I've seen them talk about it. I don't think they've implemented it, but it seems to be like in their P2 plan.
A lot of people will talk about it, like they'll describe client-side validated protocol, and there'll be like a sentence at the end, like, and you can use recursive snarks to compress the transaction history to constant size. So my work with Robin and Jonas Nick from Blockstream is to sort of fully specify a protocol with a kind of like attention duly paid to the snark part, which in my opinion is the important and complicated part of the protocol. I mean, like this is a valuable insight, but it's not new. And redoing this kind of thing in different ways is not really the hard part, as evidenced by the fact that that's the part people have done and not the snark part, which is probably harder. Yeah, so
So in the Bitcoin world, what's the coin ID of Bitcoin?
The transaction ID and the VOut.
Yep, exactly. It's just a way to uniquely identify a coin, which is the transaction ID and the output index.
So the coin can be an arbitrary amount of Bitcoin? Yeah,
in Bitcoin terminology, coin is sort of synonymous with note, which like Zcash uses, other people use. It's just an arbitrary denomination amount of money.
Okay.
Yeah, I mean there are a lot of sort of subtleties that arise when you actually try to go about doing it in an entirely client-side validated way. For example, paying fees is kind of complicated because there's no like way to put a fee on chain, right? Like, I mean, imagine like a sort of stupid example where like we had a triple and then we just added a fee. Well, how do you know the fee is valid? You need a proof that the transaction had enough money to produce the fee. So what do you do instead? Well, maybe we send a proof to, like, one solution, right, would be I pick a miner or like a block producer and I pay them the fee directly. But that is unsatisfying. So what we could do instead is maybe pass them some kind of like partial proof that leaves their part unspecified, but the rest of everything specified, and then they are allowed to claim money equal to the fee amount that we've paid them, only if they can show that the nullifier of the transaction appears in the blockchain. That's what we do, but that requires a multi-stage proving kind of technique. So the way we've written the paper uses this kind of abstraction called PCD, or proof carrying data, where you have like little bits of data and functions that act on the data. and we annotate each piece of data with proof that it was computed correctly according to this computational DAG. Which, I mean, if you squint, does actually kind of look very much like what we want to do here. But for the reason I just described in terms of paying fees, each transaction is actually going to be multiple nodes in a PCD graph. So maybe you do a proof, and then you do like another proof. And so, I guess concretely, right, how would this work? There's basically two technologies that we could use to do it. One would be recursive fry, and the second one would be like folding. So you may have heard of Plonky 2 is a proof system that is designed for fast recursion. It's very mature, it's been out for a long time. That would be one approach. That's what people would often call a Stark, because it uses Fry, which is the kind of core bit of Starks that uses hash functions and is quantum secure if the hash functions are quantum secure. And folding is a different approach where you have, I could just give a whole talk about folding, but it has lower recursion overhead, which is important in our case. Just to give you some sense of why this is important, right? Normally we think of proving and verifying as two separate things. There is a prover and then there is a verifier. The prover does some stuff, the verifier does some stuff. Usually you want what the verifier does to be as simple as possible, because at least in our world, the verifier is like a blockchain or like a very large number of people. And the prover, I mean, it could be like one really big computer, like RISC-0 or something. Like you only have to produce the proof once. In this model, it's very different. This is more like, I guess, the original applications of ZK in crypto, like the Zcash or Monero or like Aztec, right? This is client-side proving. So the clients are doing the proving, and the clients are doing the verifying. So in this example, right, the client has to like verify these, and it has to prove this. So the client runs a verifier and a prover. Here I say we recursively verify proofs. What does that mean? Well, the verifier is just a program, just a circuit, say. It is both a circuit and a program, but circuits and programs are not the same thing. We can construct a proof for arbitrary circuit satisfiability. The verifier is a circuit. We can make a proof that the inner proof satisfies the verifier. So you have a proof of a proof. In recursive Fry, we do that. We just run the prover, produce a proof, verify the proof in another proof, and continue. Folding is a different approach. So the genesis of folding in this context is, like I said, the client is doing both proving and verifying. So it doesn't actually matter that the verifier is much cheaper than the prover, because the client is always doing both of them. I mean, you don't want it to be excessively more expensive, but so folding, rather than having a prover and a verifier, has three algorithms. This prover, verifier, and decider. The prover takes two proofs and it kind of like combines them in some way. The verifier checks this combination step. The verifier does not check the proof. It only checks that you added the two proofs together. The folding scheme ensures that if this proof is valid, then both of these are valid. And therefore, you only have to check that they were combined correctly. the decider actually checks the final proof. So in a normal snark, this bit sort of doesn't exist. There's just a prover and then a decider, somebody who verifies the proof at the end. Here, we have a prover that proves that we combine the two proofs. We have a verifier that checks that the combination was computed correctly. The reason why we do this is because suppose we have like a very large number of proofs. Rather than prove, verify, prove, verify, prove, verify, we prove the combinations and we construct these individual proofs. And then we just verify this thing at the end. This is what people call IVC, or incrementally verifiable computation. And the idea is as you're running your computation, you're proving it as you go, and you're only sort of doing as little work as you possibly can in addition to constructing the proof. When you're doing recursive snarks, you're doing a lot more work. You're constructing the proof, but you're also constructing a proof of the verifier. So this is all to say that in our context, we actually don't really care about the decider because it never ends. There's just this big recursive graph of proofs, and this person verifies these, and it takes this one, it sort of adds them together, and it produces a new proof. So we're only ever adding proofs together and then verifying the combinations. We're never doing this last step where we actually verify the proof. Or I should say, each person is doing this, but you're never doing it in circuit, right? You are verifying these incoming proofs like yourself, but you never have to do that as part of the proving process. I'm not sure if everybody's following this, but this is why folding is interesting for client-side validated zkcoins type proposals. And oh, by the way, neither of these require a trusted setup, and this is like very mature. This is like off the shelf, you could do it. This is being actively worked on, but is not like done yet, I would say, but it's less mature. Yeah, I don't know. If people want me to talk about more, I can. Talk about like details of how it actually works. This is like the high level like motivations for why things are the way they are. Paper coming soon, hopefully. Yeah.
Are there a lot of people at Alpin working on the paper?
No, not me.
Or just you?
Yeah, me and Robin Linus and Jonas Nick. Neither of them are at Alpin.
They're working on what?
The paper.
Oh.
Folding is separate from your paper, though.
Folding is separate from the paper?
I think folding's being worked on with Starks as well for StarkNet, but maybe not.
I've also worked on folding, and there was recently a paper from Benedict Munz and his student, I think, or no, a bunch of people. I don't remember all the authors, but anyway, it's called Accumulation Without Homomorphism, and it is an attempt to do folding without homomorphic commitments. So when I write this plus here, it's actually surprisingly similar to what you actually do. You have like a commitment to something, and you literally add like a random value alpha times a different commitment. And because these commitments are homomorphic, this is a commitment to W plus alpha W. Notice that I moved the alpha inside and then I moved the plus inside as well. That's what it means to be linearly homomorphic. So here, this plus is saying we basically take random linear combinations of proofs. That's what this is doing. And this is great for elliptic curve stuff. It does not work at all for Frey, because Merkle trees are not linearly homomorphic commitments. What you can do instead is, so here, when I write this plus, this is elliptic curve point addition. Like it is literally elliptic curve point addition. You can abstract this and just have what you might think of as like a linear combination check. You have 3 commitments and you check that 2 of them form as a linear combination the third one. That is what accumulation without homomorphism is doing. There are some technical problems with the approach, or I guess, I don't know if problems, but like things that one might hope could be improved upon. It's not equivalent to folding because it only efficiently supports folding of small depth. There's a something that increases linearly in the depth. So here when I write it like this, the depth would be the number of times that I combine them. There's a trick you can do to reduce the depth where instead of adding them together, I add them in pairs, and then I add the pairs together. And so these, instead of doing like, right, like this, and then like this, and then there's like, see what I'm saying? You know, there's like a linear folding, like if you were to add them sequentially in order. Like these nodes are pluses, so it's like pi 1 plus pi 2 plus pi 3 plus pi 4. This would have depth n. But because of the kind of like commutativity, very loosely construed, you can instead form a tree. Say like pi 1, pi 2, pi 3, pi 4, and you add them like this. And so, in this case, the depth would be 2, and in this case, the depth would be 4. You can see that the depth here increases logarithmically. So in many cases, you can use accumulation without homomorphism with a log depth kind of folding like this, and it's fine. But ideally, one would be able to eliminate the dependency on depth entirely. I have no idea what Starkware is doing with folding. People use the word fold to refer to several different, mostly unrelated concepts in snarks. So there's like, I don't know if Waking has it on the thing over there anywhere, but in Fry, you have like, you have like a polynomial f of x, and it's supposed to be like of degree k. And we have f evaluated on some set where the size of s is equal to n is equal to like k times some factor where this is like greater than 1. So that is to say we're evaluating it on more points than its degree. And what you do in Fry is you sort of take an FFT folding. So you have, we can write it like this. Where these are the even coefficients. So you see here we have like these x's. So this would be like C0 times constant plus C2 times x squared plus C4 times x to the 4th. These are the odd coefficients. So it'd be like x times C1 plus x cubed times C3. And so we can split it into these two things. And the nice thing here is that if the degree of f is less than or equal to k, then the degree of f0 and f1 is less than or equal to k over 2. We sort of can reduce the degree by half by splitting it like this. But then we have to somehow deal with the fact that we have 2 polynomials instead of 1. So some people call this folding. You pick a random value alpha, from a big field. And then we define a new polynomial, f prime is equal to so people call this folding in Fry, but it has nothing to do with folding schemes. But it is a kind of folding. You sort of take it, you can imagine like a tree, you take the two subtrees and you add them together. So yeah, and you can kind of see how if you keep doing this, eventually you're going to end up with something that's like equal to like f naught plus x times f1. And if we fold that, we're just going to get some like, you know, f naught plus alpha prime f1. And it folds to a constant. And the kind of trick is, if this domain behaves nicely, as we fold, we can actually take this notation means f evaluated on the points of S, and we can get from this f naught f evaluated on S is somehow like equivalent to f naught on some other domain and f1 on the other domain. And this other domain is of half the size. So it's a kind of big digression, but that's what people mean by folding in Fry usually.
Does that make verification easier?
It makes the proof possible at all.
Oh, okay.
Yeah, this is crucially, like, this is essentially the main idea of Fry, at least like operationally. Like, proving that this is secure is very, very, very non-obvious and hard, but yeah, the sort of core insight is that we can take something of degree k and split it into two things of half degree, and then combine them into something that is of half degree. And we can keep doing this. If you do this log times, you'll end up with a constant. And then the trick, the hard part, is like, we only have this, right? We have f evaluated on a bunch of points. We don't have f. We don't have its coefficients. And from this set of evaluations, we want to show that it has low degree. So we've kind of constructed this sequence of things that all obey a kind of locally testable quality, right? We take random linear combinations, which given like a point of f0 at s prime and a point of f1 at s prime, we can test this like by just looking at those points. That if you take this and multiply this by alpha and add them, you get the right thing. But we also have a kind of global property going on where the degree of this should be half the degree of the previous thing. And so the magic is in figuring out or showing that if you test this at a bunch of points locally, that you can show that this actually holds.
You can see that it seems to be half the degree based on like a certain certainty, right?
Say that again?
You can, like, by testing the points, you can see that it's a low degree.
I mean, kind of. Not quite.
Like, to a certain degree of certainty, though. Yeah.
You can tell that the final thing is of degree 0.
Mm-hmm. Yeah.
You can tell that all of the intermediate things hold locally. From all of that local information, you want to be able to infer this global property of f. Yeah, so it's definitely recommend reading about it if you're interested, but I'm probably not the best person to talk about Fry soundness. So yeah, that's all I
Can I
have.
ask a very basic question?
Yeah.
So what's the difference between, very high level, what's the difference between NPC and FHE?
MPC stands for multi-party computation, and FHE stands for fully homomorphic encryption. Fully homomorphic encryption is an encrypted piece of data you can run a program on. MPC is like everybody in this room has a piece of information, and we all want to compute some function of it. And we don't want anyone else to learn anything about our pieces of information. So in some way, MPC is sort of fundamentally a kind of like multi-party thing, right? It's like a distributed sort of
Yeah, and the
thing.
MPC is split the private key to every party. No one knows the whole key. Have to combine them together and do something.
I mean, that could be an example of something you do with MPC, yeah.
And FHE can do the same.
No, I think DSA is like MPC, right? The threshold DSA is like MPC.
You can think about it like this: FHE, like I can give you a blob, and you can do stuff with the blob without knowing what's in the blob. With MPC, each party, if you set it up like this way, each party in the computation can not know the whole. Each party has a piece of the computation and can work on that, but doesn't have the whole picture, or has none of the picture, depending on how you set it up. So the God mode is FHE if it actually worked.
No, the most powerful thing is called indistinguishability obfuscation.
Yeah.
Indistinguishability obfuscation is, I believe, equivalent to all other forms of cryptography. And what it allows you to do is take a program. The definition is kind of subtle, but in spirit, it's basically this. You can take a program and obfuscate it so that I can take this program, obfuscate it, give you the obfuscated program. The only thing you can do with the obfuscated program is run it. You can't learn anything about the internal structure of the obfuscated program.
Black box.
So T.
Does that work yet?
Black box obfuscation is not possible, but what I just described is basically black box obfuscation. There's like a subtlety for indistinguishability obfuscation, which I think for our purposes is probably not super important.
So we can you actually use it today to transform?
Yes, there are papers that are written about indistinguishability
No, not papers.
obfuscation.
Like a GitHub repo where I can
No, it's not
translate
efficient.
my C.
It's not like concretely efficient enough to be useful.
Isn't there like in terms of MPC networks, there's certain other assumptions. Like there's one where only one node has to be honest to maintain privacy in a entire network. There's one where a majority has to be honest, things like that.
Mhm.
Here's an example.
It's like semi-honest and
The team I work for does TLS notary.
all of those.
Yeah.
So they split your TLS session key. So it takes two parties to compute this ephemeral key, right? Two parties are they split this key, right? And so you need both of those parties have half of the key effectively. And so to send data to the server, to actually encrypt data with that key, you have to talk to both those parties. With FHE, I have no idea how that plays in that model, but FHE, why did you ask about FHE? Do you use FHE? Do you want to use FHE? I'm just curious.
It's a buzzword, right?
Is there a use case for FHE? Like, who's using FHE today that you guys know?
I heard they're doing some voting stuff.
FHE coprocessors.
Can you name a project that uses it in production?
Yeah.
It was a
TLS notaries, we're using MPC in production today.
Some of the stuff that you would do with the TEE, you could kind of do with FHE.
Yeah.
Not everything, but some stuff. I don't know. Okay. One example is private information retrieval.
Yeah.
Private information retrieval is I have a database, and you want to query the database. Normally, you just send me your query, and the database would perform it for you. But then I know what your query is, so maybe that's bad. What you'd like to be able to do is send me some kind of entirely opaque thing. I take the opaque thing, I run it over the whole database. I have no idea what's going on. It picks out the information you want, and then it keeps it encrypted and it sends it back to you.
Mm.
This is very much along the lines of what
Keeps
FHE does.
encrypted, so can I read?
Who are you?
I want to query a piece of information.
The person executing the query can retrieve the information, yes.
Okay.
The person performing the query cannot see what the query is doing.
But that's
So what about result?
FHE?
What?
That's FHE?
it's the specific thing is private information
Hmm.
retrieval, and it is implemented with FHE.
Essentially, you need all the operations to be what's the word for it? Where it's like f of a plus b equals f of a plus f of b. You know?
Homomorphic.
Oh, that's homomorphic. Yes, that makes
Yes.
sense.
Fully.
Fully homomorphic. So not just
Well,
not just that. F of
Yeah,
a
remember
times
I
b equals
described
f of a.
previously the commitment that was linearly homomorphic, the commitment to witness plus alpha times the other
Yeah.
commitment. So fully homomorphic encryption, you want some like encryption thing where if you have like A plus encryption of B, I'll write them differently so that you don't think they're the same. You get, but also
Is that all you need? Is multiplication and addition?
yeah.
Oh, really?
And in fact, there are other ways you can do it. You can do it with some groups that are sufficient, but yeah, multiplication and addition over a field is sufficient to evaluate any circuit or arithmetic circuit over
Compute.
encrypted data.
Compute any function? That makes sense, because I read somewhere that perceptrons could emulate any computation. But I guess we're getting nonlinearity. Okay, multiplication.
Yes.
Yeah.
That's crucially important.
Yeah.
So I mean, there
You
are
have to transmit the entire like blob. Right?
What?
Like the person that wants to do computation on the data needs to get the data. It has to have the data, right? Like the whole
the
thing.
person who the
Like this-
idea is like some powerful person has the stuff you want to run the query on.
Yeah.
And you are weak, and you can't do it yourself.
Yeah.
But you don't want them to know what you're doing. So they already have the data, and they just need your encrypted stuff to work with the data.
So I encrypt the query.
Something like that, yeah. That's how private information retrieval works. There are other things you can do with that.
But like in my head, MPC actually works for like real world use cases, and beyond private information
does.
retrieval,
It
FHE
does.
doesn't actually work.
No, it is. There's a company called Zama.
There's a company called
Richard Schultz money.
KuCoin.org or whatever. Anyway, I haven't seen a good real world use case. The PIR use case, like no one cares about
So
sharing.
you can do private inference with machine
Oh,
learning.
another garbage use case, but okay.
Private information retrieval is not a garbage use case.
No one wants to share data.
What?
Like,
No, the reason why you want this is because if I'm really lazy and you are a Bitcoin full node, and our Bitcoin is not a great example, but suppose you're like a Monero full node or a Zcash full node, and I want to query my UTXO from you, but I don't want you to learn what my UTXO is. And I'm very lazy and very weak. I can't do anything with the chain, so I use you and I use private information retrieval to get my data from you, and I keep my privacy. So this is a real.
is that implemented today? Does that work?
There's a block explorer that uses private information retrieval so that when you query it,
Okay, there's one use case.
Wow.
No, I said private inference. For real use case. People do not want to reveal their inputs for medical applications if you're doing like medical diagnostic with machine learning.
I do think one aspect of FHE that is often underestimated, and that maybe this isn't like a fair characterization of people who really know what they're talking about, but just in the popular conscious, is you usually want ZK with FHE because you want to make sure that the powerful person who's running your program is actually running your program. They're not doing something else. So you often want some kind of a snark construction paired with the FHE so that they prove to you that they did the right thing and got this result. Otherwise, you can do a kind of chosen ciphertext attack type thing where they send you garbage and see how you react.
Yeah, that's a big problem.
FHE coprocessors.
Or you could just use a TE for that instead of FHE, but you still need ZK. What?
I put a link to a block explorer that uses private information
Is it
retrieval.
open source?
I don't know.
Better, thank you.
You're welcome.
Checking.
Yeah, there's lots of really interesting exotic types of encryption that maybe you aren't aware of, like witness encryption or functional encryption or indistinguishability obfuscation.
Yeah, it is open source.
All fun stuff to read about.
Differential privacy.
Differential privacy, yeah, that's also that's
Yeah.
cool thing. Witness encryption is like I can encrypt something to the solution to a problem. So I can be like, if you can find a Hamiltonian path in this graph, then you can decrypt this data. Which is pretty neat. I mean, maybe a more like concretely useful example would be like if you produce a Bitcoin transaction that has some property, then you can decrypt the information. So it's actually keyed to the solution to an NP problem. Functional encryption is like you have some encrypted data and you can only execute a function on it and get the result of executing the function.
Well, I thought functional encryption was where you would encrypt the function itself.
There are a bunch of different variants. Honestly, I don't want to say the wrong thing, but
I know, you know Kathy So?
No.
PSC? She was working on like a form of functional encryption for machine learning, essentially.
Oh, cool.
Yeah. I think it was like a ZK technique, I'm not really sure. But basically the idea is like you want to be able to commit to a model
Mhm.
without revealing the weights, and also be able to not prove the model right correctly.
Oh, interesting.
Yeah.
Okay.
Yeah.
No way. That thing he just linked, they're using enclaves and GPUs.
Isn't that great?
Like who is this team? You know them? Bliss?
No, I don't know.
Oh, cool. That's dope. That's like next level researchy. Bitcoiners can do things.
I don't think these guys are Bitcoiners.
Oh.
It also, it's not working. I'm trying to search for an address and I keep getting network error.
This is the problem with FHE, bro. We've been led astray. They've been pitching FHE since I was a kid.
They've been pitching TEs since you were.
They've had them, and they've just been actively attacking you.
They've been broken.
FHEs just add, subtract, multiply, and divide.
Well, probably not divide.
But just like use all the things.
What?
Like you said, you have like there's ZK plus FHE prevents the auctioneer from seeing
From doing the wrong
doing
thing.
badness.
Yeah, all of these things compose, I think, in really interesting ways. And ZK seems to have like really come out far ahead in terms of like rate of progress. But I hope that all of the other things continue to improve as well, so that we can get this like non-linear.
I feel like you're gonna get a boost in MPC in the next 2 months, and then FHE in the next 6, because there's all these crazy.
That's a very aggressive timeline.
Well, because everybody's going to Japan to do this MPC residency, and this is like, and then the guy that wrote the book, Jonathan Katz,
Mhm.
he's doing a conference in Singapore, MPC Con, and like all those people get together, and then you get one of these like all of a sudden all these tools come out because all those brains meet up, and that's
I mean,
happening.
people have been working on MPC for a long time.
Right, but now that you get, I think the combination of like funding, like from startups using it, and then researchers knowing that like there's like a tighter loop now, feedback.
Yeah, well, I think one of the reasons why ZK accelerated so much is because blockchains are like the perfect application.
Blockchains kickstarted like they brought secure enclaves further than academia ever could because of
How do you
like,
feel about that?
dude, like for the first 10 years enclaves were like you're on your own, and then with the support of like Puffer, I don't know what Puffer Finance does, but all these people in the cryptocurrency space, they needed them to prove that they were not evil. So the tooling has improved for TE.
I don't know. I mean, you know, like maybe you're being silly, but like I do think that the synergy between ZK and blockchains is really remarkably perfect.
Yeah, it is.
I think MPC and FHE don't
It's not-
have
no,
quite
but-
the same product market fit.
No.
And I mean,
Oh, you say PMF?
yeah.
Startup? Yeah, no, you're right. I agree with that.
But
Yeah,
maybe
you're
they
right.
will. I mean, there's lots of things as they improve that become feasible. So
That's Ali's story. He used to be a professor.
Mhm.
When he do a talk, no one cares. He's doing lots of ZK stuff. Until one day he talks about Bitcoin stuff using ZK, lots of turnout or something. Then he did his first like Zcash.
yeah, he's one of the authors of
Yeah.
the Zero Cash.
They
paper.
become like successful or something.
I would say so.
Then he become like full crypto guy because it's useful. It's all ZK stuff. That's his start.
Yeah.
Hmm. Encore, encore.